Hey guys, okay, we're going to finish up our topic 12 today, talking about topic 12.2, nuclear physics. A lot of what we covered in SL, you'll need as a background for this. For instance, I remember Geiger and Marsden were actually working with Rutherford to shoot, I don't know where that came from, where they were working to shoot particles through gold. It was really gold, thin gold foil, and that's how they came up with the structure of the atom. There's a nucleus and then electrons going around it. All right, I just wanted to put this up here so that you could remember. Let me see. I have this. There we go. Let me get it back up here. There we go. All right. All right. So today we're going to finish up talking about topic 12, quantum and nuclear physics, by talking about nuclear physics. Talk about all the quantum stuff in the last few presentations. This time, we're just going to talk about nuclear physics, and a lot of what you learned in SL is important here. So just go back and look at topic 7 and refresh yourself with that. But I wanted to put this slide up here to show you a reminder of how we came up with the structure of the atom by shooting alpha particles through gold foil and watching how they were reflected off. And the vast majority of them came flying through. A few of them came bouncing off at different angles, and from that they could figure out that there's a solid nucleus within the atom, and then far out from it are electrons floating around. Okay. So once we figured out what the shape of an atom was, and we using quantum physics, we have calculated the radius of an atom. What's the radius of the nucleus of an atom? So again, they would fire alpha particles at the nucleus of an atom, and because it's got two positive charges in it, and all of these positive charges in the nucleus, there would be a Coulomb repulsion, and would come in with a certain velocity, certain kinetic energy, get close to the nucleus before those forces repulsed it and pushed it back. Okay, so we use the Coulomb equation for the energy that is experienced by this alpha particle as it gets closer to that nucleus. Okay, now at this moment, at R naught, the alpha particle will stop just for an instant right here before it takes off back. So at that moment, the kinetic energy of this is equal to 0, right? It says so right here. The kinetic energy is equal to 0. So in our equation, we have the we have the overall energy. I can't underline it because it's, there we go. The overall energy, kinetic energy plus potential energy, well, this is 0. So our potential energy is given by this, by the Coulomb energy, and the charges here are the protons, right? A proton has a charge of E, 1.6 times 10 to the minus 19th, and the alpha particle has 2 of them, so it's 2 times E, and whatever nucleus that we're firing at here, whatever that nucleus is, it has a certain number of protons, whatever number of protons it is. If it's a carbon atom, it has 12, right? And so we would substitute 12 in there. And so, and this is that minimum distance radius that we're looking at right here. And so when we look at this, we put this out, we end up with the energy that this is experiencing right here, right there, is 2z times ke squared over r naught. Okay. All right. So what do we do with that? We can actually use that to figure out what the radius, or get a good idea of what the radius of that nucleus is. You notice that the alpha particle does not come in and actually touch it. So we're not getting the exact nucleus size of this nucleus. So let's just use this to give us an estimate. All right, so the energy of this, let's see, we've got this starts out with initial energy of 2.75 mega electron volts. All right, so that is the kinetic energy out here at infinity, far enough away that the Coulomb repulsion forces don't affect it. And so that's what our potential energy, our maximum potential energy is. Well, as we know, when it gets in here and stops, all of that potential energy has been converted in, I'm sorry, this is kinetic energy. All that potential energy, kinetic energy has been converted into potential energy at this point. And so that is equal, the potential energy is equal to 2.75 mega electron volts. We need to change those electron volts into joules. So we multiply by our conversion factor, and we end up with 4.4 times 10 to the minus 13th joules. So that's the energy that's going on here. And so we know this equation that we had just derived on the previous slide, and we can use it to solve for that. All right, we know this. We know that we are talking about a silicon nucleus that has 14 protons in it, so we can substitute in 14. This is a constant, this is a constant, this is Coulomb's constant charge. So we substitute those in. 2 times 14 times Coulomb's constant times the charge squared divided by the energy, and we get an estimated radius of that nucleus at 1.46 times 10 to the minus 14th meters. It's actually pretty straightforward. You just have to remember that all the kinetic energy is getting converted into the potential energy at this distance, and the rest is all constants. Okay, now then, if we want to find it more accurately, we can use this equation. We're not going to derive this equation. You just have to take IB's word for it that this is correct. I don't know why they would mislead you. And we'll universally use R naught as 1.2 times 10 to the minus 15th meters. Okay, so that's what we're using. Oops, I went backwards. All right. So using this, find the radius of a gold nucleus. So this is the radius that we're looking for. This is R naught, which is given right here, and it will always be given to you. If it's not given to you, this is what the value is. So you need to know that, but just know they'll probably be giving it to you. Thus, the radius of the gold nucleus is, and we substitute everything in, this is 1.2 times 10 to the minus 15th. A is the atomic number, 197 raised to the 1/3. And that gives us 6.98 times 10 to the minus 15th meters. Much closer to being accurate particle size. Okay. So here's a sample problem. Show that the density of a gold nucleus is about 2.3 times 10 to the 17th kilograms per cubic meter. All right, so we're going to use the equation. This is density equals mass divided by volume. All right, we have to derive. We're going to have the mass of the proton. We're going to have the volume. We're going to need to calculate that. So let's see what we got. So the mass of the nucleus is given by pretty much on average the number of protons divided by the rest mass of a proton. And the volume of the nucleus is given by 4/3 pi r squared, because we look at the we look at the atom as being a sphere. So we use the volume of a sphere. And since we have r3rd, if we look at our previous equation, we look at our r equals r naught times a to the 1/3. Well, if we take r3rd here and we raise this into a third, we get r naught third to a times a. Much easier to deal with and raising things to the 1/3. And so we substitute that in and we get the volume is equal to 4/3 pi r naught cubed over times a, times the atomic number. Okay, so substitute all of that in to our density equation, and here's our representation of mass given up here. Here is our representation of the volume given right here, and you notice that the A's cancel out. The atomic numbers cancel out, and that means that every atom has this radius, which is an interesting, or I'm sorry, has this density, which makes sense because it's all protons and neutrons, and they're all the same regardless of where you are in a nucleus. It's all protons and neutrons, so they should have the same density. And so we substitute in what we have, the mass of a proton times 4/3 pi. This was the r naught that was given us, raised to the third, and we end up with a density of 2.3 times 10 to the 17th kilograms per cubic meter. This is an incredibly high number. It is. I once heard somebody describe it as 1 teaspoonful of this density material would equal the weight of a battleship. I mean, it's just, or an aircraft carrier. I think an aircraft carrier, and it's just an incredible amount of mass, and it makes sense when you look at a nucleus of an atom. There's very little space in the nucleus. It's all matter. So there we have that. Okay. Okay, so we've shot a alpha particle and calculated the approximate size of the nucleus based on its coulombic repulsion forces. We've used a non-derived, just given to us equation to calculate it, but we can also do it through diffraction. And the interesting part is, if you shine light at an atom, the nucleus acts like a slit. Okay, and what happens when you have a slit that you shine light through? It diffracts, and you get can basically use the equation that we use for diffraction. Sine theta equals the wavelength of that light divided by the distance of the light. From basically, we're talking about, if you remember, we have the central maximum, first minimum, and that's the distance that we're talking about. Okay, so let's use this in a problem. We have a beam of 80 mega electron volt neutrons that are diffracted upon passing through thin lead foil. The first minimum of the diffraction pattern is measured at 12.6 degrees. And remember, well, this is in degrees. Watch out for the radians. That should be in radians. Estimate the diameter of the lead nucleus. Okay, so we know that up here lambda equals sine theta in radians not divided by times d, right? We also know it equals this, and we know the mass of a neutron. Okay, so we can calculate the energy 1/2 mv squared, right? I'm sorry. We have the energy right here. We're going to convert it to joules, and so we get 1.28 times 10 to the minus 11th joules. Okay, this is the kinetic energy of a neutron that is moving really fast based on its momentum. And so we want to calculate its momentum. We find out that it is, that's not it, that is momentum squared. So we take the square root of that, and we get momentum is this meter seconds. And then we can substitute that in up here. We know Planck's constant. We've calculated the momentum. And so all we have to do is divide. Planck's constant divided by our momentum gives us a wavelength of 3.207 times 10 to the minus 15th meters. Now this is in the gamma radiation area region. So this is a very high energy photon that we're talking about here. And nuclei are just like electrons. They absorb and emit certain radiation packages. We don't call them photons, but what they emit is extremely high energy, much higher energy than electrons do. So, because there's a whole lot more forces and things going on inside of a nucleus. So this is the wavelength, very, very short wavelength of the light that is being diffracted. So now we can substitute that in here. We have the angle, and we need to do this in radians, and we have the wavelength, and so we can calculate, just substitute in 3.207 times 10 to the minus 15th divided by sine of 12.6 degrees in radians, and we get 1.47 times 10 to the minus 14th meters. So that is the d is basically the radius of the nucleus. Okay, it's the size of the slit, basically. Okay. Okay, so size of the nucleus, we've covered that. How different ways of calculating the radius of it. So there's more than one way to skin a cat, and that is there's more than one way to calculate the radius of a nucleus. Some of them are pretty much just estimates. Some of them are pretty accurate. All right, so let's talk about decay. We talked about the half-life in SL, and we're going to keep talking about that, but let's talk a little bit more about what's happening, a little bit more conceptual, and apply that a little bit. Okay, so every time you have a population, it's got a half-life and it's decaying, and as it's decaying, the population is getting smaller. So as that population gets smaller, the decay rate gets smaller as well because there's less and less material there for it to decay with, and you get the famous exponential distribution that we talked about in SL. So we can represent this as this graph line, this exponential, as the current population, the amount of the current material that we have left, equals the original population times e raised to the minus lambda t. Lambda is the decay constant, and t is the time frame that this decay has happened. Now, as you'll see in different slides, sometimes t is equal to the half-life, and that makes things very interesting. And I mean that sincerely. It does make things very interesting. Okay. So the decay constant is not a universal constant. It depends on the material. And so sometimes you're either given it or you have to calculate. Okay. So here's a sample. Now, this is something that IB would expect you to derive. And they want you to derive, this is what they're basically saying, derive this equation right here. Okay, so we're going to start out with the equation that we just talked about. Okay, and then when t equals the half-life, this is what we start out with. Our current population is equal to the initial population divided by 2, because half-life, that means half of it is gone. Okay, so n is just n over n naught over 2. And so we substitute that in to this equation. So n naught over 2 goes over here. And look what we can do. We can cancel out the n naughts, and we end up with 1/2 equals e to the minus lambda over t. The capital T stands for half-life. Should be written in there, but it wasn't. All right, so next thing to do, let's just take the natural log of both sides. And we end up with natural log of 1/2 equals negative lambda t over 1/2. Okay, we move the negative over to this side. That's just a math trick. And so what we do, I was getting myself mixed up here. We invert this. What is, we take the negative out. To take the negative out, negative ln 1 over 2 equals ln of 2. And here you can see where we're about to solve our little problem here. And so the half-life is equal to natural log of 2 over the wavelength. I'm sorry, wavelength. Lambda in this case is the decay constant. So it's lambda, it's natural log of 2 divided by the decay constant. So if you know the half-life, you can figure out what the decay constant is of your material. Okay, so there's an example. Half-life of uranium-238, and that means 238 nucleons, is 4.5 times 10 to the 10th years. And for iodine-123, it's 13.3 hours. Find the decay constant for each of these. All right, so there's our equation that we just derived. We can bring it in. We know what the half-life is. It was given to us. We do not need to worry about the units unless we need to convert it for some other reason. But we can go with whatever units they give us. This equation works. So ln of 2 is 0.693. It's just a constant. That's just what it is. Divided by the half-life is all it is. Do the same thing for I-123. And there you see the decay constants that were derived for each one. So this is important. What you're looking at with the decay constant. The decay constant is a probability. It's the probability of decay of a nucleus per unit time. Okay, so it's the probability that so much of this nucleus is going to decay over a given time, and that's whatever that given time is right there. So if we converted this to seconds, then we would convert the probability to some other number per second. Okay, that's all it is it's just a probability. Okay, so we measure decay with a Geiger counter, and we put it in units of becquerels. There's other units out there, but IB is using becquerels, and that's 1 decay per second. So we have this equation, which again we are not going to derive. It's just this is what we're given, and this the activity. This is not atomic weight. This is activity, becquerels, decays per second, is equal to the change in the population over time. It's also equal to the decay constant times the current population, and it's equal to this whole thing right here. All right, so we can use any one of those. So that explains what each one of those are. And this is saying that this is true, which is when you substitute that activity equals decay constant times the population, you can substitute that in here to derive this equation right here from this. You can derive this equation from this one using that.